All right, good afternoon, everybody. Let's get started. So today we've reached an exciting milestone. Today we are going to learn how to actually build a basic RISC-V processor using everything that we've learned so far. So let's get started with that. So how does one go about building a processor? Actually, sorry, before I get started, let me just tell that there have been a bunch of questions on Piazza about quizzes. If you didn't get your quiz in recitation, you can go to Sally Lee, who's our course administrator, and pick it up from her, and her office number is in the course website. Okay, now let's get back to this. So the von Neumann model. So all modern computers are based on what's called the von Neumann model. And what this refers to is a computer that looks like this. It consists of three components. The first is main memory, which is responsible for holding both the program and the data that the program uses. The second is a central processing unit, which basically accesses and processes the memory values and produces any results that need to be stored. And finally, there's the third piece, which is how we deal with the outside world. So how do we deal with inputs and outputs? So this third part we're going to get back to in 6004 in a couple weeks. Today we're going to focus on the left two over here. Okay? So what we're going to do today is basically learn how to go ahead and build this central processing unit. So what's the key idea behind what von Neumann suggested? So what he suggested is that you should express programs as a sequence of coded instructions, okay? And both your instructions as well as your data should live in memory. So here's an example of what your memory might look like. And so a portion of it is going to be is going to be used just for instructions, and another portion of it is going to be used for data. And then our CPU, which is kind of the brains, which is communicating with this memory, is going to figure out what to do with these instructions and what operations to perform at every cycle. So what does an instruction look like? An instruction consists of a bunch of different fields, right? So here's, this is just a dummy example, but basically you'd have a 32-bit encoding of an instruction, which would tell you a few things about the operation you're trying to perform. So the first is some encoding of what operation you're trying to do. Are you trying to do an add? Are you trying to do a shift? Are you trying to do, some kind of comparison function? And then the next three are registers. And so we need to know where our operands are coming from. So RD stands for destination register. And here I've just used some random input registers, calling them RS and RT. So what is this translating into? Basically, I want to run the operation up on my registers RS and T, and the result of that should then be stored into register D. Okay? Now what about the data portion of my memory? The data portion of my memory is just a bunch of bits. Okay? So you might ask yourself, well, for starters, how can I tell the difference between, the bits that make up an instruction versus bits that are just data? Any ideas? Well, as I mentioned, sure. Exactly. So that's what we do, is we basically allocate different portions of our memory for the instructions and for our data so that we can tell them apart. All right, so let's take a little bit of a closer look at this central processing unit. And so we've divided our central processing unit into two portions. We have a data path and a control unit. And you can think of the data path as the portion that's accessing the data in main memory, and the control unit is the portion that's accessing the instructions. So let's elaborate on each of these. So what's the data path doing? The data path is kind of the muscle. It's doing all the hard work in order to do your computations, whereas your control unit is the brains behind everything. It's figuring out what it is that I need to do. So what is the data path typically look like? Well, you know from the assembly programs we wrote at the beginning of the semester that essentially the way that machine language works is that you have a bunch of registers and you can perform some operations on them, and then you store the results back into another register. And so that's what this picture here is showing us. So here we've got a bunch of registers, and then we've got two muxes, which are selecting our two source operands for our ALU. And then our ALU is going to perform some function that we tell it to perform on those two operands. And then the result is going to basically come back up this path. The destination is going to specify which of the registers I want to enable for writing. And then the result is going to go into the register that I enabled. Okay? Now, on the other side, what do we have? We have a bunch of instructions. So the first thing we have to do is we have to have a special register, which we call the program counter, which is responsible for telling us where in your instruction sequence you're currently located. Okay? So the program counter is basically a pointer into our instruction portion of the memory, and it says, it points at the next instruction that we want to execute. And the instructions are all encoded, and so even though they refer to, an operation and then certain source registers and destination registers, all of that gets encoded as a bunch of zeros and ones, and so we need to understand what those zeros and ones mean. And so one of the major parts of building this processor is to build that logic that's going to decode these instructions and tell the data path what it is that it needs to do. All right, so now let's think about what are instructions? So we've already said instructions are basically our fundamental unit of work. And each instruction consists of a few things. The first is the opcode, and the second is the source and destination operands. And essentially what we're going to do when we execute an instruction is we're going to repeat this loop for every single one of our instructions. So what is this loop doing? It's telling us how do you go about executing an instruction. So what do you do first? First thing you do is you fetch the instruction that the program counter is pointing to from your instruction portion of your memory. Then you decode that instruction in order to figure out what those ones and zeros correspond to in terms of operations and source operands and all that. Next, you're going to go ahead and read your source operands. Now you're going to actually execute the operation that it asked you to perform. Then you're going to write the destination. And finally, you're going to compute what the next PC value is going to be. Okay, so typically in a program where we don't have control flow, what do we expect our next PC value to be? If my words are 32 bits, which is 4 bytes, what is PC going to be set to? Yep.
PC plus 4.
PC plus 4, exactly. So most of the time, all we have to do to compute this next PC is to increment PC by 4. But then we have to have some special cases when we have control flow instructions, and we're going to see how to deal with those. All right, so how are we going to go about building this processor? What we're going to do is we're going to start, with our basic ALU operations, and we're going to see what the data path needs to look like for those. And then we're going to augment this data path in order to support more and more of the instructions that are part of the RISC-V processor. So what are we going to do? We're going to first of all recall that we have 3 different types of instructions. So the first set of instructions are ALU instructions, or instructions that use the ALU to compute some value. The second set of instructions are load and store instructions, which access our main memory. And the third are branch and jump instructions, which actually change the control flow. So those are going to be the type of instructions that make the PC potentially not be, the next PC not necessarily be PC plus 4. All right, and so what pieces of hardware are we going to use to build all of this? Well, here are all the pieces, all of which you're familiar with. So we're going to have some registers, we're going to have some multiplexers, we're going to have our ALU, which you can just think of as a black box at this point. This is basically the ALU that you built in Lab 4. And then we're going to have a register file and some memories, okay? So we'll get into all of these as we proceed. All right, so the first thing I want to do is just clarify a little bit what do I mean by a register file? Because in our sequential logic lecture, we learned about registers, but we didn't really, talk about having many registers interacting with each other. And so basically, a register file is just a bunch of registers, and like the picture that we saw a couple slides ago, the additional thing that it has is input and output ports, okay? So the register file that we're going to use for our that the RISC-V processor has 2 read ports and 1 write port. So what does that mean? It means that a single instruction can read 2 different registers and write yet a 3rd register, or it could actually, read and write to the same registers if it wanted to. And so these multiplexers are going to specify, their select value is going to say which one of the registers is my source for port 1. This one is going to say what's my source for port 2. And then my write address is going to say which of my registers is the one I want to write to. Okay? So let's take a little bit of a closer look at what one of these registers look like. So this is basically just a register that's a D flip-flop with an enable. So what does that enable do? Anybody remember? Yep.
Tell us whether D should be stored in the flip-flop.
Exactly. And that's what this picture here shows us. So we have a flip-flop. It's storing some value. And it's just going to keep storing the same value until the enable is set to 1. Once the enable is set to 1, then on the next rising clock edge, we're going to get a new input, and that's going to now be stored into this register. Okay? So basically, what this register file looks like is that the write address is essentially selecting which one of the registers should have its enable set. Okay? Whereas the other ones are just going to maintain their old value. All right, and so here's kind of a block diagram of our register file so that we can see all of the inputs and outputs that we have to work with. So let's go through each of these in detail. So as we said, it's a 3-port register file, which means we can read 2 different sources and we can write 1 source. And so we start off with the read sources. So what do we have to do? We have to say which registers am I trying to read. Now how many bits do I need in order to specify which register I want? If I have 32 registers, I need how many bits? 5, right? So my register address fields are 5 bits. So I have 5 bits for my first register, 5 bits for my second register, and then what comes out on the data side is the value of each of those registers. Okay? Then I have my write side, and so for the writing, I have a write address, which again is 5 bits to say which register I want to write to. I have a write enable, which is saying, am I actually permitting a write to the register or not? I have the write data, which is the 32-bit value I'm going to write to that register. And finally, we have our clock. So how does our register file work? This is the key, okay? Reads are combinational and writes are clocked, okay? So let's see what exactly that means in this timing diagram. All right, so what's going on here? So we're going to start off looking at a read operation, okay? So what do I have here? I've got a read address, A, that becomes available to me at some time. And then some propagation delay after I got that address, I'm going to be able to read the contents of register A on my read data port. Okay? Any questions about that? So that's a combinational read, okay? Now, what about my writes? Okay, my writes are clocked. So what does that mean? So first of all, recall that in order for something to satisfy, to work properly as a sequential circuit, it needs to be stable for T setup before the rising edge of the clock and T hold after the rising edge of the clock. Okay, so here we've got our rising edge of the clock. And we basically see that all three of our inputs, the write enable, the address, and the data that we're trying to write are all stable for T setup before the rising edge and T hold after, okay? So what's going to happen if we satisfy that criteria? What's going to happen is that some propagation delay after the rising edge of the clock, we're going to see the new value that we wrote here as the value that comes out from our register A data port. Okay? Is that clear? Great. All right. So now, what happens if, we're trying to write to the same register that we're trying to read? Are we going to read the new value or the old value? What do you think? We're going to read the old value, okay? So basically, remember that the reads are combinational. So as soon as I try to read this RA1, I'm going to get its current value, okay? I then go ahead and produce a new value, which I want to write to potentially that same register, but that write is not going to happen until after the next rising edge of the clock. Okay, so you read the old value, and then at the next rising edge of the clock, plus some propagation delay, you write the new value. Okay? All right, what about our memory? So, for now, and this is very much an oversimplification, but basically for Lab 6, which is where we're going to be building this processor, we're going to assume that our memories behave just like our register file. Okay, so what does that mean? It means that our loads are combinational and our stores are clocked. Okay, now in reality, memories don't really work like this, and so for Lab 6, you're going to see our memories referred to as a magic memory, okay? And by the end of the semester, when we deal with our design project, we're actually going to be building realistic memories. But all that this magic memory means, it's still behaving just like a memory, except that we're saying that it's able to give you the response within the same clock cycle that you requested it. Okay, so that's the assumption right now. And so next week we're going to be learning about a whole bunch of different memory technologies, and as we continue with the class, we're going to augment and make our memory more realistic. And as I mentioned, in the design project, you're actually going to change your memory to use a real memory rather than this magic one. Okay, now we're ready to get started. So here's an ALU instruction. It's a bunch of bits, and I imagine that by just looking at these bits, nobody has any idea what this instruction is trying to do, or at least I hope you don't. So how do I figure this out? All right, so what I need to do is I need to understand how these bits are split up into different fields in order to make some meaning of them. So if you look at your reference manual, which is your instruction set architecture sheet that you also got as a cheat sheet for quiz 1, we're going to continue to be using that. And so what that's going to tell us is that these bottom 7 bits are always the opcode. Okay? So every single instruction, you're going to first look at those bottom 7 bits in order to figure out what type of instruction it is. Okay? So in this particular case, we have this opcode that's 0, 1, 1, 0, 0, 1, 1. And so our manual basically tells us that this is an op type of instruction, which has an R type of encoding. And so let's make that a little more understandable. So all that means is that it's a 2-register type of ALU operation, okay, which has a particular encoding that you're going to follow. So as soon as I know that that's the type of encoding that I have, I can now understand what the rest of these fields mean. Okay? So in the case of a 2-register ALU operation, this is what those fields mean. Okay? So specifically in this example, I'm going to have this function 3, which is all zeros, function 7, which is all zeros. My RD register is saying that I'm going to write to register 3. And these zeros are basically telling me that the operation that I'm going to perform is an add. And so I'm going to write to register 3. And which registers are my source registers? What is this encoding telling me? My RS1 is X2, and my RS2 is X1. So what's the instruction that's being performed here? This is basically add X3, X2, X1. Everybody comfortable with that? Great. Okay, so now let's go ahead and start building some hardware. So we said that there's basically this loop of things that we have to do in order to process each of our instructions. The first one is that we have to figure out what our instruction is, and by fetching it from our instruction memory. And so from now on, we're actually going to treat our instruction memory and data memory as 2 separate memories. There's no reason why you can't implement it that way. And so just to keep things simple, we have one memory that's for instructions, another memory that's for data. Okay? So what gives us the address of the location that we're trying to fetch from in our instruction memory? It's this special register called the program counter. Okay, so the program counter, initially it's going to point to our first instruction, and then we're going to have a little +4 adder, which, for regular operations, all it's going to do is increment the PC by 4. And we also show you here a little bit of reset circuitry, just so that you'll remember that we do have to somehow initialize this PC when we get started. For the rest of the slides, I'm going to leave that out just to make the slides a little easier to read. Okay, so what happens? So I send this value, this PC, which is my address that I'm trying to fetch from my instruction memory, and what comes out is the data at that location. Okay? The data is a 32-bit value, and some of those bits I can essentially use directly in my data path, right? Because we saw that, my source registers and my destination register, they're going to be directly encoded in that instruction, and so from there I can just use those bits as my address for my register file. Okay? Other bits I'm going to have to actually take a closer look at and perform some logic on them in order to figure out what the data path has to do and potentially create some additional control signals. Okay? So this is the fetch portion of executing an instruction. Okay? This is what we do for every single instruction we want to execute. Now let's see how we need to augment this data path. Let me just give you a little more. This is actually what I already said. So we have the PC as the address. We add 4 to it each time if we're not doing control flow instructions. And then we can decode the different fields from the instruction that we just read from our instruction memory. All right, so now let's start, thinking about what do I need in my data path in order to support all of the instructions that exist in my 32-bit RISC-V processor. So here's a list of 2-register ALU operations. Okay, so right off the bat, we see that all of these instructions actually follow exactly the same format, right? They each have 2 source registers, RS1 and RS2. They have RD as their destination register. And the only thing that differs is which operation the ALU is going to perform. Okay? And so the encoding of these instructions is going to be exactly the same, except for the part that tells you the ALU operation. All right, so what's going to happen is we're going to group all of these instructions into a a type of instruction. For the 2-register ALU operations, we call them the op type. Okay? And so the information that our instructions need to give us are what's the ALU function and what are the 3 registers that we need to access. All right, so let's start augmenting our data path here. So first thing I'm doing is I'm adding this register file, which we just learned about, right? So it's a register file that has 2 read ports and 1 write port. And I'm getting the address fields directly from the instructions, right? I have my RS1, my RS2, and my write address, or my RD, coming directly from particular bits in the instruction that I know is how a 2-register ALU operation is encoded, okay? So what else do I have to have here? Well, I can go ahead and figure out, that the operation that I want to perform is going to be based on some of these other bits. So specifically, I know that the general form of any instruction whose opcode begins with these 7 bits is going to do this. So it's going to be a 2-register operation. I'm going to perform some operation on those 2 source registers, and the result is going to go into another register. Okay? So the first thing I have to do is I have to figure out, well, what is the operation that I want to perform? And so I'm going to look at these. This is F3 stands for function 3, which is just because it's 3 bits wide, and function 7 is 7 bits wide, and together those are going to tell me exactly what function I'm going to execute. In reality, the F3 is by itself is going to tell me almost everything that I need, but sometimes we use the bit 30 to get some additional information. So, for example, if you're trying to differentiate between an add instruction and a sub instruction, your F3 bits are going to be the same, but your I30 bit is going to differ. Okay? Similarly, if you are trying to specify a shift-right logical or a shift-right arithmetic, the F3 encoding is going to be the same, but the bit 30 is going to tell you which of those 2 operations you're trying to do. Okay? All right, and so now I can go ahead and read my source operands from my register file, and we're going to bring in our ALU, which is the ALU that we built in Lab 4, and all we have to do is tell the ALU which function we want it to perform based on interpreting what these bits are telling us. Okay? Everybody comfortable with that? Terrific. So I already have a way of specifying my source registers. Now I know how to get the operation I want to perform. I've already specified my destination register, and so I'm going to take the output of this ALU and I'm going to feed it back as the write data from my register file, and I'm going to say write enable register file. I'm going to say in this kind of instruction I want to enable writing to my register file, and so I'm going to set that to 1. Okay? All right, so let's take a look at the data flow for these 2-register ALU operations. So it's basically what I said. The first thing we're going to do after fetching the instruction is we're going to read our 2 source operands. Then we're going to pass the ALU function to the ALU. It's going to execute that function on those 2 operands, produce a result. We're going to set the write enable to 1, and that will cause the result that's on this wire to be written to the destination register. Okay? Looks good? All right. So this is our data path for about, 12 instructions or so. Not so bad. So let's continue this process. Okay? So the next set of instructions are the ALU immediate instructions. So these are pretty similar to our 2-register ALU operations, except that now, instead of having my second source be from a register, it's from an immediate value. Okay? So we call this immediate I because we have a bunch of different immediate encodings, and so all all ALU with one immediate operand instructions are going to use the same type of encoding for their immediate. And so the only thing that differs, once again, between all of these instructions is what ALU operation we need to perform. Okay? So let's go back to our hardware, and remember that this time all we have to produce is once again the ALU function. We need our destination register, our source register, and this time we need to also decode this immediate value. All right, so here's my data path before making any modifications, and here is what an ALU with immediate instruction looks like. So once again, the opcode for all of these instructions is exactly the same. All right, so this opcode, it tells you that it's an ALU operation with one source register and one immediate operand. Okay? Once I know that, I know how the rest of the fields are encoded, and so I can figure out the rest of the fields that I need. So specifically, notice that the RD field and the RS1 field are actually in the exact same bits of my instruction. Okay, so this is a pattern that you're going to see repeated over and over again. Okay, this is what makes, this processor a RISC type of processor, where part of its simplicity is the fact that that we can basically reuse the same hardware in order to decode different types of instructions. Okay, so the same bits that gave us RD in our 2 ALU instructions are also going to give us RD in the ALU with immediate instructions. Okay? And so basically these bits coming up here for RS1 are exactly the same as what I had before. So I haven't changed anything in my data path so far. Now, what does my ALU instruction with immediate do? Well, this is what it performs. Okay? So it does a sign extension of this 12-bit immediate that's encoded in my instruction in order to turn it into a 32-bit value. And once I have two 32-bit values, it does the ALU operation on them, stores it into register RD. The only situation where things are a little bit different is where the operations are shift operations. So what's the largest that it makes sense for our shift to shift? If I have a 32-bit value, does it make sense to shift 33 bits? No, right? So I'm going to shift somewhere between 0 and 31, which means I only care about the 5 lowest bits of my immediate, which tell me what that shift amount is in the case of shift instructions. Okay? But the encoding is just the same. All right, so now once again, I'm going to use the F3 field and I'm going to use the instruction 30-bit in order to tell what my ALU function is. Now notice that instruction 30 is only used in the shift operations where this upper portion of my immediate is actually not being used. Okay, so I can use it instead to encode, am I doing a left shift or, a logical shift or an arithmetic shift. All right, so what do I have to add to my hardware to make this happen? Well, I'm going to add a multiplexer. Okay, so my multiplexer is going to say, in the case where I have 2 source registers, my ALU is going to get its second operand from the register file. In the case where my second operand is an immediate, I'm going to get it from this other input of my multiplexer, where that input is basically the sign extended immediate that came directly from my instruction. Okay? And how do we go about doing sign extension in hardware? Anybody know? You would basically look at your most significant bit and make all the bits above it be equal to that most significant bit. Okay? So you're going to take this immediate 11-bit and copy it all the way, up from 12 to 31. Okay? All right, so let's take a look at how we run one of these instructions. So Similar to before, we have one source coming from our register file. Now we have the second source coming from this immediate value, and so this bSelect signal has to be set to 1 in order to tell our data path that it should be reading the constant or immediate value rather than the second register. Okay? We then have an ALU function which tells the ALU what operation to perform, and finally we set write enable register file to 1 in order to enable the writing of the result to the register file. Okay? So far so good? Great. Okay, so we're done with all of our ALU instructions, which is the majority of our instructions. Now we have a few more to deal with. So the next type are the load and store instructions, okay? And here it tells us, what exactly needs to happen for load and store instructions, and we're going to look at each of them individually. So each one of these is going to need to actually access our data memory. And the encoding, you notice, for each of these is actually quite different. And so we're going to treat each of them as its own instruction type. Okay? So what do load instructions look like? Load instructions have, once again, their own opcode because it's its own type. And so this opcode corresponds to a load word instruction. And then what is going to actually need to be done in our data path is we're going to read the contents of register RS1. We're going to add to it the sign extended immediate, and then we're going to use that as the address into my data memory. And whatever I read from memory is what's going to ultimately get stored into register RD. Okay, so let's make all of that happen. So some of this, as you can tell, looks familiar, right? This RS1 plus sign extended immediate is something that already exists in our data path, right? So we can go ahead and use the ALU just like we used it for a register immediate ALU operation in order to compute the address of this load instruction. Okay? So what do I need to add to the data path? Well, I certainly need to add a data memory. And the operation that my ALU is going to do is always going to be an add immediate operation. And the immediate is coming from the exact same bits that the immediate came from for an ALU with immediate instruction. Okay? So what do I have here for my data memory? Let's take a look at what I've added and how the data flow works. So specifically, the first thing that I do is I get one source register plus my immediate value. I then do a plus B operation in my ALU, and that produces my address for my data memory. Okay? The data memory is then told that it should do a read operation, and so that results in putting the contents of that address on this read data port. And now I've added a multiplexer over here to show that sometimes I get my data from the ALU, sometimes I get my data from my memory. Okay? And so now I'm going to have to select where it is that my data is coming from in order to write it back to the register file. And so for a load operation, I'm going to want this WD select to be 2 in this particular multiplexer. Okay? And then the rest is as before, where the output of this multiplexer feeds in as the data that I'm going to write into my register file. And once again, I need to set my write enable to 1. Any questions about that? Yes?
Can you explain again why it's 2, the WD select?
So I have 3 inputs in this multiplexer because I'm going to, as you might guess, have yet another input that's coming in soon enough. And so the input, that 2, just corresponds to the wire that connects the read data port output from my main memory instead of 1, which corresponds to the output of the ALU. So in this case, what's coming out of my ALU is just the address of the instruction I'm trying to, of the data that I'm trying to access in memory. right? It's not the actual value of the memory. So I have to do two things. I need to use the ALU to first compute that address. I then feed that address to my data memory, and then the data memory does a read, and it returns the value that I'm trying to load. Okay? And so now the value that I write back to my register file is this one that came from the data memory, not from the ALU. Good? Other questions? All right. So let's move on to a store. So once again, the store is its own type of operation, and this opcode tells us that it's a store word. And here's what a store looks like. Okay? So it's got some similarities and some differences to our load instruction. The first is that we're using, instead of the RD register, we're using the RS2 register, because that is the source for where, what's the value that we're going to write to our memory. Okay? And as I mentioned before, we always want the RS2 bits to come from the exact same location in our instruction. Okay? So what does that mean? It means that instead of having these bottom 5 bits represent my second register, I actually am using these 5 bits to represent the register that's going to give me the source of my data. And now I still need 12 bits of immediate in order to produce the address. And so all I do is I take my 12-bit immediate and I divide it amongst these 2 other fields. Okay? So once again, we're trying to get as much overlap as possible in our implementation so that the hardware that is required to execute all of these instructions is minimal. All right? So what I'm going to need to do is, once again, I'm going to need to produce, an address for my memory. And the way that I'm going to produce that address is by running an add I instruction in my ALU. But now, the value that comes in to this multiplexer is a little bit different, right? Instead of being the sign extension of the top 12 bits, I'm going to take these bits plus these bits, concatenate them, sign extend that, and that's what I'm going to feed into this one input of my multiplexer. Okay? So I'm just forming my constant a little bit differently. And so what do I have to add to my data path? I need to add 2 things. First, the value that I'm going to store into my memory is coming from RS2. And so I have a path from RS2 to my write data port of my memory. And secondly, I need to have a new input into this mux, which is going to produce the correct immediate that I need for the address calculation in a store operation. And once I've got that, then my data flow looks just like before. The only difference is now my bselect is 2, because my immediate is being calculated a little differently than before. My ALU function once again says go ahead and add these 2, the register plus that special immediate, which we'll call immediate S, to indicate that it's an immediate for a store operation. And that produces the address that is fed to the data memory. And this time, instead of reading from the data memory, I'm going to tell the data memory that I want to perform a write, and the value that I want to write to it comes from my second source register. Okay? So just the last thing to note here is, in the case of a store, do we want to write anything to the register file? No. So what do I have to set this write enable register file to? I have to set it to 0. Okay, this is critical, right? There is going to be some kind of data on this wire. So it's very important that I make sure that when I'm executing a store instruction, I'm not enabling this data to be written to whatever, address happens to be on these wires. Okay, because otherwise I would corrupt some register value. Okay? All right, almost there. I'm not sure we're going to get through all of it, but almost. Okay, so the next type of instruction is branch instructions. So once again, all these instructions look the same. This time we're going to have yet another type of immediate calculation. And what we're going to need now is a slight addition to our ALU in order to be able to do these comparisons. And instead of producing a 32-bit value, I just want to produce a Boolean, which says take the branch or don't take the branch. Okay? And so to do that, we're basically going to augment our ALU with a second ALU, which we'll call the branch ALU. And all this is going to do is, depending on the function that we're trying to do, it's going to compare A and B. So if we're doing the greater than function, it's going to say if A is greater than B, then branch is true. Otherwise, branch is false. Okay? So we're going to take this, additional ALU and basically augment the ALU that's in our data path to consist of the original ALU, which does 32-bit computations, plus this new ALU, which produces Boolean results. Okay? So let's go ahead and put that new ALU into our data path. And so now what do we need in order to execute branch instructions? So once again, hopefully this part's getting a little old. We have a particular opcode which identifies this type of instruction. And so all branches have the same opcode. This is what a branch instruction needs to do. So it's going to first compare the contents of register 1 with register 2 using this branch function. It's going to produce this immediate value, which is yet a third form of an immediate value. And the result is that the PC is going to get updated. If the branch returns true, then you do PC plus this immediate. Otherwise, the PC just gets the PC plus 4 value that it always got before. Okay? So let's see what we're adding here to our data path. We're adding this extra little adder, which takes as one input the PC, and as a second input this immediate B, which our decoder is going to produce. And it's going to give us what the branch target is. Okay? Now, in addition we're going to add this multiplexer over here to indicate that the source for the next PC can come from different places. So either it's PC plus 4 in the case where we don't take the branch, or it's set to 1 in the case where we do take the branch. Okay? And so what is the last thing that we have to remember here is, just like the store instructions, the register file should not be updated in any of the branch instructions. Okay, so it's also critical to remember to set that write enable register file, or just the enable of the register file, to 0. Okay? All right. These are the last 3 instructions, of which I'm only going to show you one, as the rest you can figure out. And doesn't include anything new. And so we're going to focus on the jump and link register. So the 2 jump instructions actually modify 2 registers. They modify the PC register and the destination register. Okay, so let's take a look at how this happens. So here's my op type, which indicates that it's a jump and link register operation. And this is what I need to execute. So my destination register, remember, this is how we're doing the linking. It's going to store the PC plus 4 value so that if I call a procedure, I have a way of coming back, right? So it's remembering my return address or whatever else. But in any case, that's what happens in this RD gets PC plus 4. And my PC is basically going to the value that's inside this register plus the immediate that's encoded in this instruction. And once again, the instruction here is the immediate follows the same format as an immediate I, which is the ALU with immediate instruction type of format. Okay? And so we already have a data path that produces that type of immediate. And we know how to add that immediate to the register. And so all we're going to do is we're going to add some additional logic, which is going to say, which is going to take the PC+4 value and give us a path for writing that to the register file. Okay? So I now have my third input here, which is what can update my register file. I have another input for where the next PC can come from. And let's take a look at the actual data flow. So the PC+4 value comes through here. I set WD select to 0 this time, and I set write enable to 1. That's going to take care of updating the RD register to be PC+4. Okay? Then I'm going to do a register plus immediate. I'm going to take the result of that, and that's going to become my branch target, or sorry, my jump target, which is an unconditional jump, so I always update PC to take that value if it's a JALR instruction. Okay? So, to summarize, what we're going to actually be building in Lab 6 is you're going to instantiate each of these components that we just talked about: an instruction memory, data memory, PC, and a register file. And then you're going to basically develop two functions. The first is a decode function, which is going to take the instruction that you fetched from your instruction memory, and it's going to get all of these fields that we care about, right? So it's going to tell you which source registers to read. Then we'll read those values from the register file. And now we're going to have an execute unit, which basically consists of our ALU plus a little bit more logic. And it's going to compute the operation that we decoded coming from the instruction that says what was the ALU operation or the branch function or any of that. And then we have a few additional things, right? So here's the extra path for the PC. And then the execute function is going to produce a few outputs. It's going to say, what register am I writing to? It's going to say, what data am I producing? And in the case of loads and stores, it's going to produce an address. And finally, my register file can be written either from the output of the ALU or from the memory. And notice that that will also cover from the PC case. Okay, so this is the picture you guys are going to see in Lab 6. And you're going to go ahead and implement basically these two functions, which are described a little bit more detail in the next two slides, but really in detail in Lab 6. Now, last thing I want to say, which is the following. When you're done with Lab 6, the coolest part about 6004 is that everybody gets a RISC-V Inside sticker to place on their computer. So when you finish that lab, make sure to ask one of the course staff for that sticker and proudly represent it on your computer. The only reason I don't have it on mine is because I just got a new computer, but it will be there soon. All right, thanks everybody.